Okay, so we're going to look at another example problem here. Obviously, the problem just magically appeared at the beginning of the video, but it is an op-amp, and we'll discuss how we're going to go about doing this here. I will want to emphasize here first, I haven't drawn any power supply on the op-amp because really to find the transfer function, we don't need a power supply. We have some power. We only need the power supply if we have a specific input voltage or an input signal to know whether we're going to saturate the op amp or not. So when we're looking for a transfer function, we don't really need what the voltage rails are for the op amp. Now, before we also get into this here, this is going to be something that I'm going to put down and then erase here because this is going to lead us into the next chapter here. Well, actually, the next kind of, I shouldn't say chapter, the next set of lesson plans here when we're going to kind of finish up the course information with talking about filter design. Now, a short thing here is to remember that the impedance of a capacitor is negative J omega C. So at low frequencies, caps are opens, meaning they behave as open circuits. At high frequencies, and I'll put the low in quotes too because that really depends on the size of the capacitor and the actually also not just the capacitor but the the size of the capacitor, but also then obviously the frequency you're operating at, because low frequency could mean kilohertz, low frequency could mean hertz, so it really just depends on the circuit that you're looking at and the application. So high frequencies, caps are shorts. Now the reason I point this out then is at low frequencies, this capacitor right here is going to act as an open. So that means Vin isn't even getting to the op amp, so Vout's just going to be 0. At high frequencies, this acts as a short, so this will be a short, so Vn is going to get into the negative terminal, but then this 4 microfarad capacitor is going to act as a short, which basically means then that this feedback path this resistor is going to be shorted out, and I'm going to just have a short going back to the negative terminal. So that means at high frequencies, the output's going to be 0. So there's going to be some mid-range frequencies where Vout is not 0. So this is actually what we're going to call a bandpass filter. Now, it's a special type of bandpass filter, but it's a bandpass filter. Great. So again, that's something we're going to talk about in more detail in the next upcoming lessons. But I like to kind of start introducing these concepts when we start hitting it, because one of the first things we're always going to want to do in our filter analysis here is know what the transfer function is. That's one of the reasons, not the only reason, that's one of the reasons we want to know and understand transfer functions. So I'm just going to erase all of this right now, just so that I can keep the circuit there as I start working on the problem. Now, remembering from our previous lesson, now technically you don't have to do it this way, but I like to do this. Remembering from our previous lesson that an easy way to find H at S is equal to V out at S if we set V in at T equal delta at T. And remember, we call this the impulse response. So again, if we do that here, I'm going to just let this be delta at T. And then, of course, just like anything, we're going to do a Laplace transform of this. So this goes to 1. And then let me pull out my calculator here, because I'm going to do the 1 over SC of these. So 32 microfarads, so 1 divided by 32 exponent -6. And this is where I sometimes like to just use the k thing. So this is going to be 31.25 k over s. And then this 4 microfarad would be 250k over s. Now, again, we want to look at this and not think about, oh, I've got to do nodal analysis. I want to think about back to circuits 1, to some of our basic kinds of things. This looks like a circuit we know, and I'm going to draw some circles here, and then I'm going to erase them again. If I look at these things here, I could look at this as being a ZI and this being a ZF. And so then V out is simply just negative ZF divided by ZI times V in, because this is just an inverting, and I'll put that in quotes, inverting op amp. And the reason I put it in quotes is it's not really an inverting op amp, because an inverting op amp just has the 2 resistors. And so with these capacitors here, we're actually, as we had said at the beginning of this video, it's actually a bandpass filter. But with circuit analysis, with steady state and with Laplace transforms, we get to still treat everything as if it was, quote, a resistor, which makes the analysis easier. Okay, so let me erase some of these just so I can clean up the figure a little bit. So let's erase those here. So now we just need to compute what these are here. And I'll do ZI first, because that is easy. ZI is just 250 plus 31.25 k over s, because they're in series. Okay, ZF is, I wouldn't say hard, but it's a little bit more challenging. These are in parallel, and because it's a symbolic expression, it's in parallel, I'm going to go ahead and do the fact that this is going to be 250k over s times 10k divided by the sum. So actually most of my work is going to be spent here figuring out what ZF is. Now I'm not necessarily going to clean it up 100%, but I am going to clean it up some here. So first off, I am going to clean up ZI just a tiny bit here. I'm going to rewrite ZI as 250 s plus 31.25 k, and then this is all over s. And clearly what did I do is I just multiplied this by s over s. And you'll see why in a second why we'd want to do something like that. Now I need to clean up ZF here. So ZF here, well, first thing I'm going to do is actually I'm just going to do one thing here. I'm going to multiply this by s over s. And so ZF is, well, it's 250k times 10k, which I'm going to just leave that as 250k times 10k. I'm not actually going to multiply that out, because we'll be able to simplify it in a second. And this would be 250k plus 10k times s. Whoops, my hand caught that. Now I say we're not going to multiply it out, because let's think about this for a second. Let's look at this. Factor out a 10k. And I just had a total lame-ass TV show reference here that I'll share with you guys. So I used to watch this show. It's a zombie show on Sci-Fi. I don't even remember the name of it. gosh, that's going to bother me. But anyway, there was a character on the show called 10K, and if you've ever seen the show, you probably know what I'm referring to. If you haven't seen the show, you can just say, Professor Rumsey's kind of an idiot. He watches silly zombie shows on sci-fi. But yeah, back to the problem here. So we're going to factor out a 10K. So if I factor out a 10K, what do we have here? Well, let's continue it in blue. 250K times 10K over, well, I'm factoring out a 10K, so I'd have 25 plus S. Well, life has just been very kind to us. And of course, I'm being a little silly, but it has been very kind to us. Why? Because these 10Ks cancel. And so this, of course, simplifies the expression. Now, there's a reason why I left this here, because we know that my transfer function here is going to be ZF, which is 250K, over S plus 25, divided by Zn, which is 250 S plus 31.25K over S times Vn, which is of course 1. But then by simplifying it like this, well, remember, if you're doing complex fractions here, this is just h at s would then be 250K over S plus 25 times S over 250 S plus 31.25K. So we essentially have my transfer function here. Now we are going to do a couple things here. I'm going to go ahead and remember our rule of thumb is we want to have just an S in front of these terms. So I'm going to factor out a 250. So I'm going to factor out a 250. So my h at s would be 250K times S over S plus 25. There will be a 250 out here in front. Oh, and you're probably all screaming at me because I forgot one very important thing back here. There should absolutely be a negative, 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 right? Because this is inverting, which is very important. I'm kind of flippantly saying, it's only a negative. It's obviously very important, and you guys, many of you have probably suffered losing a silly point on an exam before for forgetting a negative. So they are very important. And then if I do 31.25K divided by 250, we get S plus 125. And then simplifying this finally, we get 1,000, because it would just be 1K, 1,000 S over S plus 25, S plus 125. So the numbers actually worked out pretty nicely just by keeping track of things here. And so this is my transfer function. So this is part A. Now part A is where all the work is. Part B, computing the zeros and poles, should be trivial. You should be able to just look at your transfer function. If you've done all your work correctly, you should be able to look at your transfer function and just write those answers down. So the zeros, well, there's only one. It's S equals 0. And the poles, there are two. S equals negative 25 and s equals negative 125. Now, that is our answer. Now there's one more thing I'd like to kind of bring up here to kind of bring this story here to a full closure here. So this is something, again, we'll be examining in our next set of videos here. So we're going to be looking at something eventually called a Bode plot. And a Bode plot, of course, is we're going to be plotting the magnitude of the transfer function evaluated at j omega. So just except that's what we're going to be doing. And we said that this is going to be a bandpass filter, so it's going to look something like this. That's what it's going to look like, except it should be flatter across here. And there's going to be these two cutoff frequencies. And this is omega. These two numbers, and we'll go into more detail, have a lot, a little excessive with my underlines, to do with the poles. So what those two numbers are, those corner frequencies is what we call them, or cutoff frequencies, have a lot to do with the poles. So again, that's one reason we are interested in poles. It's not the only reason, it's just one. Now this does wrap up, this wraps up circuit analysis with Laplace transforms. It's not that we couldn't do more. I mean, we could do more examples. We could even find a Thevenin equivalent with a Laplace transform, but I'll be honest, I can't recall where I've ever used a Thevenin equivalent of a Laplace transform, unless it was because a problem told me to. As far as practical statements, I've used transfer functions all the time. As I said, in controls or in advanced filter design, I use transfer functions all the time. But I haven't necessarily used the Thevenin equivalent in the Laplace domain. It's not to say that it's never used, I just haven't used it, and that's just more circuit analysis, which we've already done. Alright, so this wraps up our circuit analysis with Laplace transforms. Then we're going to be moving on to filters.